question about overloaded operators and conversion constructors. So, like when we do a constructor which takes a single parameter, it's like a coming in conversion.
Yeah.
An operator data type is coming out conversion.
Yeah, that'd be converting to and from.
What if you have two classes, like book class and video class, and you want to convert the book to a video? What kind of approach would you use in that particular scenario?
Well, the constructing, let's say a date. Actually, let's experiment a little bit. So we've got
So basically, my question is, the operator data types, are they only meant to be used for POD types, or like just primitive data types put in? If you would like to convert,
yeah, that's why your question prompted me to bring this up. I believe the answer. Have you tried it?
No, I haven't.
I believe the answer to the question is yes. The conversion operators are reserved to built-in types. However, I'm uncertain enough that I wanted to try it, so that's what I'm doing right here. Holy smokes. I'm not doing my job. They're having a lot more fun over there. Thanks. I appreciate the vote in my favor. Book. No, I want to go the other direction, I think. So 18 through 26 delete. Let's put book first. And let's, that's strange. Why is that not? Get rid of this. And what I want to do is I want to convert a date to a book. And I'd say operator book date : book. And this would return book. Oh, no, I got it in the wrong place. There you go, it works. So the question was, you can certainly create, if I have a date class, I can certainly create a conversion constructor for a book, meaning that here this converts an integer to a date. It certainly makes sense that you could create a conversion constructor for a book. What I was a little unsure about is whether you'd get away with creating a conversion operator to a book. So if I have a date, to convert it to a book using this, just as there's a conversion operator here to convert a date to an integer, can you convert a date to a book? And the answer to that question is yes. So you can go both directions with any type. All right, so let me move, I'll leave this, yikes. Let me move date.cpp to convert date to book.cpp. And then let's talk about talked a little bit about this last time. So stole a bit of my thunder last time. That's all right. We'll go ahead and introduce it. I say OF stream out file. We'll call this data.dat, I guess. We will, to it, we will write hi. We'll write world. We'll close it. Oops, out F, out F, out F, dot close. G++, standard equals C++11, flush e.cpp, we run it, that creates data.dat. I can go ahead and look at the contents of data.dat. I'll bring it up in an editor. And there it is. No surprises. I'm going to come over here, change this to a new line, compile it, run it. Oops. And absolutely no difference between lines 10 and 11 and 12 and 13. However, let me go back to my original. If I now here add a line of code that says let's cast the number 1 to a float pointer, and then let's dereference that and assign 3.14 to it. That should, assigning 3.14 to memory location 1 on my machine should cause this thing to gloriously crash. It does. However, if I look at my data file, it's still the same as before. Now I do this. Try the new line instead of the end line. Compile, run, cat, and it's empty. So again, we talked about this last time, but what then is happening with the end line that is not happening with the new line? Just shout it out. Yeah.
Flushing the stream.
Flushing the stream. Right. So where is it prior to being flushed? Generally. Use in a buffer. Right. It's in a buffer. So what I can then do is I can come here. That, draw this, that'll work. Alright, so here's my buffer. And what I'm writing out is, oops, sorry. Hi, space, new line, world, space. I didn't intend for that space to be there. I didn't need either space. I'm going to take away the spaces. Sure we are in agreement that it otherwise functions exactly the same. So hi world with new lines after each. So we have hi, well, let me use a different color. Hi, there's a new line character here, world. And then with the end line version of it, we actually get hi, and then the hi flushes out and the new line is flushed out to the screen. And with world, with end line, we get world flushed out, and then the new line is written out directly. It's a little bit beyond the scope of the class, but I want to emphasize what's happening here, that underlying all of this is a system call. Another subtle hint that you're going to want to take 540 to become system call ninjas. There's nothing magical about C++ or the bash shell or any program you've ever run on a Linux box. Every one of them that is written to the screen has called this function right here, or a variant of it. Okay? It takes, you'll notice the first argument is a file descriptor. What we've all heard in other classes is that there's standard in, standard out, and standard error. Turns out that under the hood, it's number 0, number 1, number 2. Simple numbers refer to these streams. So when it's flushing to the buffer, or excuse me, when it's flushing the buffer to the screen, it's using these write calls here, writing out to 1, which is standard out. It's giving an address, so this is addressed to somewhere in memory, and a number of bytes. And so if you put 10 here for number of bytes, it'll be 10 bytes starting at that location that get written out to the screen. Okay. And actually there's a tool, I won't show it off right now, but there's a tool called strace where you can run strace on an application. You can see every single system call that's being invoked. I don't think I'm not going to do it. I have too much to talk about. But you can look at strace and it'll dump volumes and volumes and volumes for this simple program. And you will be able to, if you sifted through it, you would find actual write calls to file descriptor 1 with the H, the I, the new line, and all the rest of them. So why do we have the buffer? What is the utility of having a buffer? Yeah, it certainly allows you to kind of store it up. What is the advantage to storing it up? Right, in the absence of a buffer, so keep in mind that what doesn't have a buffer is C-error. So C-error is like C-out, except this diagram doesn't exist. There is no buffer. Character by character gets written out. Say that again? Not so much. You would need to have access to the buffer to change it up. At this level, anyway, you don't have the ability to change it up. Once it's written to the out F, then it's written.
I think it would be probably for efficiency analogous to washing the whole car at once rather than just part of the car at a time, letting it dry and doing the same process.
Yeah, I would say yes. So I don't know that I'd use a car analogy. I'm more of a truck driver myself, but efficiency is the general reason, because it's expensive to connect to a device and interact with that device, whereas it's relatively inexpensive to shove things into memory. So the efficiency argument is, rather than having 1, 2, 3, 4, 5, 6, 7, 8, 9 individual interactions with the output device, I wait until this thing fills up, and then it's just one write out to the device, and it's much more efficient for that reason. So efficiency-wise, CERR is a lot less efficient than cout. But what is the advantage to CERR? Again, we talked about this a little bit, but why is it advantageous to have an output stream that doesn't have a buffer? Yeah.
Because you want it to show immediately in case your thing crashes or whatnot.
Exactly, because when I made this thing crash and I looked at it, I went, oh man, it never even reached line 12. All right, so that's why you want CERR. Particularly, I mean, and I love to just put debugging statements in, but I'm always writing to standard error instead of standard out for that reason. If there's a crash, if there isn't a crash and I'm just doing another debugging, then I guess cout's fine. All right, so what's ENDL doing? You said it already. It's flushing the buffer, right? Let's actually take a look at that. Let's type C++ ENDL. Here it is. Let me zoom in on it a little bit. Okay, if we read here, inserts a new line character and flushes the stream. Its behavior is equivalent to calling OS. So OS is our output stream. So there's a put member function for all those streams, including cout. You can say cout.put, a new line character, and then they're making a nod towards larger character sets. And then os.flush. All right. So we can go ahead and write that function. Let's look at, here is, I can actually copy that and paste it. Let me start. So it's basically written for you in those comments. Go ahead and give me the writing for it again. Help me write the function. Right. There you go. Right. There's a programmer somewhere who at some point in time wrote that for ENDL. And then there is, note that this returns an O stream, so return OS is in there as well. All right, now I'm going to table this. I'm going to come back to it in about 1 or 2 minutes. What function is being called on line 15? Yeah.
Is it O stream by reference operator less than?
Right. Okay. So it's this operator has been overloaded for O streams. We can look at that. So let's look at. Oh, give me something to click on here. Yeah. Okay. Thanks. I was scrolling fast because I was expecting a long list like this, but of course I needed to click on it. Right here. I copied that. Let's see what it says. So there's a value to be formatted and inserted into the stream. String : open close. Magic happens to turn the 64 ones and zeros that comprise val into 3.14. For this, obviously it's generic, but I'm for the sake of the commenting, I'm honing in on this right here. Write them to the buffer. Directly or indirectly. And then the last is a return. What am I returning? An O stream. Where's my O stream?
Dereference this.
All right. Give that man one of the stuffed animals who got the ring over the little bottle at the carnival. Yeah, right? That's what all this is a variant of cout.operator chevron. So that's what was happening. So cout is being dereferenced. An address to cout is what this is, and then we just dereference it and return it since line 13 indicates that an O-stream reference is being returned. All right. What about this? Let me confuse your world. You're comfortable with line 25, didn't even have to think about that. What's being called on line 28? No, in the same sense that this was calling line 13. What is this calling? I don't have it down yet. So yeah. So this ENDL is what's sitting here, but that's not my question. I'm honing in on that right there. Now, one thing I can tell you is that I'm able to go like that. So I know that the result, I can chain them. So we know that the result of this expression is that an O stream is returned, right? So I can, let me actually copy and paste this. Let's start with this. So it's going to return an O stream. It is going to be called to all this. So what we're left with is that clearly ENDL is not a float. What is ENDL?
A function, perhaps a function pointer.
Ah, function pointer. All right. Now you gotta close your eyes and go all the way back to that union stuff we were doing days ago. What is it? Help me with the function pointer. What kind of? Let me go up here. Let's look at the function. There's the function prototype right there. So help me create a pointer to that function, and I will call it pointer. So if I asked you to create a float called pointer, you'd go, oh, like this. I don't want a float. I want a pointer to this kind of function. Just start telling me things and I'll type.
Well, first, the pointer should be in parentheses and a star just before to make it know that it's a pointer, not a function returning a pointer to an O stream.
All right, I'm happy with that much. What else do I need? So there's your return type, and then these are the function parameters, right? Like that. All right, so if we follow the pattern of thought, line 15 is how we print out a float. If I do the same thing, this would be how it prints out. Let me zoom in here. That is how it would print out ENDL. Well, let's take a look.
There it is.
Yes, definitely when you get into the hardcore programming, pointers of all types plague you.
Could you do a type diff?
You could do a type def, yes, but we won't because we We're like the weightlifters who don't use the machines. We're all free weights, so no type defs for us. All right. How do we write this? All right, we wrote, hey, I don't want a comment that says magic happens. I want the actual code for this one.
Let's
So what we need to do is we need to call the function that's on line 8. Yes?
yes. So
Which is, we have the address of the function on line 8 in pointer on 25.
what? So we should dereference the pointer to get the function out of it.
How do you call a function from a function pointer? Here's my challenge to you. Here's a function. Here's a pointer to the ENDL function. How do I call that function without regard to the stuff below? Let me give you something different. Here is a function, a pointer to the add2 function. Help me call the function. Yeah, there you see, it's so easy. Help me call this function. Yeah, of course. What about we got to put something inside it? Here we have to put in 2 integers. What do we have to put inside here? Refer to line 8. Ah, an O stream. Okay. So let me grab this. Let's throw it down here. And I'll leave that there for posterity. I have to put some O stream inside here. Now, I actually don't have this quite right. It's not called ENDL. What is our function pointer? Right. So what's the O stream?
This. It's this.
Actually, I get rid of that. That's what the function pointer is. Right, now I can look at that. You see there's no name here. What was the O stream for the function on lines 15 through 23?
What the color is, whatever the color is, if it happens to be C out or C air.
Right. So we don't know, but we do know that this points to the object calling the function, and we know that it is an O stream calling the function. How do we know? Because this is a member function of the O stream class. By definition, an O stream has to be calling the function, or something derived from O stream. Now I could do this, but we're clever and we know that ENDL is returning whatever was being passed in, right? Here's OS being passed in, it's returning what was passed in. So coming here, since it's returning what is passed in, I can just, yeah. There you go. So let's move it forward a little. Oh, that's actually
Namespace csci511.
This already exists. We used ENDL. Why don't we write our own function? Screw ENDL. So all we have to do is we have to follow this rule here. I'll use this as a model. So I'll say lines 8 through 13 yank. And we'll put it right below ENDL. And we will call it the Magnificent 7. And what we'll do is the Magnificent 7 will Let's have the function do that. Let's use it. First I got a lot of crap in here. I'm going to have to comment some of this out. You know, rather than commenting all this out, I think what I'll do is I will all right, now I just delete the stuff that I don't need. Okay, let me make sure that everything I have here so far compiles. And it does. All right, so now let's go ahead and run it just to see. Prints 3.14 twice. That's fine. So let's say cout chevron. Let's add a space. Chevron. The Magnificent 7, chevron, I don't know, another space, the sky is blue, 489, that's the number I thought of just now. We can print out the Magnificent 7 again. Let's add an end line. Oops. And we'll add another end line. All right. So we've written our own manipulator doing that. Let's look at our PDF. So let's see if I look, where am I? There we go. So this is our end game for what this needs to look like. Right. So this right here, stamp stream. We're going to be using inheritance. You want to hazard a guess what stamp stream inherits from?
O-stream.
Yeah, O-stream. That's good. And you look at all of this stuff below it, and it raises the question, oh man, how am I going to write code for that? How am I going to write, I could maybe see writing code to print out this string, but how am I going to write code to take a 64-bit number and send a 3, a dot, a 1, a 4, a 1, and a 5 out to the stamping press? And even this thing here, let me pause for a moment. What do you think the signature to this looks like? That there is probably a function pointer to a function that returns an O-stream reference and takes an O-stream reference as an argument, just like ENDL, right? Well, that right there is a little bit of a giveaway, and this stuff's so obvious it doesn't give itself away. All of the functions here have already been written to do all that. You don't have to do any of this. It's all been done. When you inherit a class off of media, all of those functions, the compare call number, the compare title, all that you're inheriting and you just use. You don't have to change it. In fact, you can't change it, right? They're not virtual. So we just use them as is. And that's the case here. When we look at O-stream, all of this functionality is already written. We don't have to do any of it. In fact, I'll hazard a guess that your definition for this class is going to be somewhere in the neighborhood of 2 to 5 lines, depending on how you like to space things. There's almost nothing to it. So let's look a little bit closer at this kind of stuff then. So end row is like end line. In fact, I don't need to focus on end row. I can focus on end line. Let's look at end line and what it's doing again. So let me do back a couple times, and I think it'll appear. All right, here it is. Let's look at this flush. So again, this is they kind of among terms here. We have a basic O stream and a no stream. We just call it a no stream. So a no stream has a flush function. Key word here is synchronize. To synchronize means to bring into sync the application with the output device. Right? So when I look at this diagram, as long as hi world is in the buffer, I am out of sync. For me to synchronize is for me to take all this stuff and dump it out to the screen. So that's why they're using the term synchronizes. Synchronizes the buffer. Controlled output sequence is a fancy way of saying the output device. Internally, you have to sift through some stuff that isn't that important. Here's the key verbiage. If everything's good, then it calls pubsync on its associated stream buffer object. And that is the key. So I click on pubsync. Note, I'm not in the OStream class any longer. So what happens is flush is calling a function on a different class. Flush is a member function of OStream, and inside that source code, it's calling a function in a different class. So now it's worth it to take a closer look at see if we can find a good kind of partial to this one. It's drawn a bit wonky, but all right. So strictly speaking, as an inheritance diagram, they got the arrows wrong. The arrows should go up to the base class. So this is saying that iStream is actually derived from iOS, as is OStream, and iOStream is derived from both of these. Okay? So keep in mind that the arrows are backwards. The process they went through to create this hierarchy is the exact same process that we went through in the library application. They looked at common data, common interfaces, common behaviors, and abstracted the common stuff up. Okay? So what we have is we have our OStream. And we have, based on this, we have something called a stream buff. That's another class. And there's a relationship between these two classes, some sort of pointer. I'll just say PTR, and that pointer points to the stream buff. Okay, so the OStream has a function called flush, and flush calls pubsync, and pubsync is a member function of stream buff. And the reason they're able to call each other is because of this relationship. There's an internal pointer it has. Now, what stream buff does, let's go ahead and follow this just a little bit further. calls a protected virtual member function sync. And this, to me, this is what the game's all about. So, take a step back. I talked a little bit about this last time. You all have finished the library project. You've cashed in on the millions of dollars you made on it. Now you're living on an island somewhere. But some poor guy has been assigned the task of maintenance on it, and they need to create, he's got a whole shipment of DVDs from the now bankrupt Blockbuster Video that they need to inventory. And so this poor guy on maintenance has been tasked with creating a DVD class. They're going to derive the class off of media, and when they look at media, which functions can they create their own versions of? So I'll give you a hint, they cannot create their own version of compare call number. But what function can they create their own version of? There are a few of them, yeah.
Compare other, display.
Compare other and display, I think, are two of the prime ones. And why did you identify those as two that you are allowed to create your own version of?
Because they are pure virtual.
Because they're virtual. Now, if it's pure virtual, you have no choice. You have to create your own version of a pure virtual function if you want to be allowed to instantiate an object. But if it's virtual, that in essence is an invitation to create your own. Okay? That's one key thing. So it says virtual function. That's an invitation to create your own. This, I think, is equally illuminating. And in our library class, all of the functions were public, right? But if it's protected, what does a protected specifier mean exactly?
That is the right classes to share the variables.
Right. So it's like private in that the outside world doesn't have access to it, but protected specifically still hides it from the outside world, but specifically says derived classes are able to see it, right? And that is tremendously illuminating because that means if someone made it protected, it is them saying, hey, if you're going to derive a class off me, these are the things you want to look at. These are the things you're probably going to want to create your own versions of. Now I can look at StreamBuff. So I don't think I want to look at basic StreamBuff. Let me look at StreamBuff. Let me zoom out just a little bit. I guess I have to look at, nope, there it was. StreamBuff. All right. So there's some public member functions, some buffer management, without looking too carefully. Right here. We really want to focus in on this section because this is saying if we're going to derive our own class from it, these are the things we're going to be interested in. And I actually need to, let me come back here. We are creating stamp stream, or stamp stream, and we're going to create StreamBuff. And there is an inheritance relationship here. I didn't give myself much room, but you create your own version of OS. You derive off of OStream to get stamp stream. That's so that you got this right here. The benefit to that is you got thousands and thousands of lines of code that know how to output things. StreamBuff we are very interested in, and the reason we're very interested in it is because of that sync function. Let me first where is sync? Right here. Okay. This is a protected virtual member function of StreamBuff. So it's very much encouraging us to write our own version of it. What sync does, synchronizes the contents in the buffer with those of the associated character sequence. This this right here is what's called, this buffer they're calling a character sequence. So I take I draw some ephemeral, I think this light gray is a nice ephemeral color. Right, this is out there in the mall. This is our stamping press. Is that readable? Yeah. I mean, you can see it. I don't know that you can read my writing. There's some sort of software. Well, actually, let's call that software library. What are the kinds of things that we call on? What we need to do is we need to take this H and get it out there, and then we need to take this I and get it out there. And what are the commands available to us to get an H out to an aluminum plate? Set die and stamp, yeah? So there are going to be a bunch of calls to set die and stamp. What we are doing when we do that, when we call set die and stamp several times for this high world, what we are doing is we are synchronizing with I can't remember the damn terminology. We're synchronizing the contents in the buffer with the associated, with those of the associated character sequence. All right, I mixed up my terms just slightly. We are synchronizing the H, the I, the new line with this when sync is called. Now, let me make it clear that virtual, it probably returns something. I don't know what it returns, but the function is called sync, right? It's a protected member function. They're encouraging you to derive your own class, as I've shown here. I called that stream buff. I should have called that stamp buff. You have to write your own sync function to get the stuff here out to here, meaning that what you're going to have inside the sync function you write are a bunch of set die commands and a bunch of stamp commands. Because the creators of the OStream class and the stream buff class years ago, they didn't have any idea of your needs for synchronizing. So they created a virtual function and said, you write it. When you originally start, before you start, you need to insert a plate, and when you're done, you need to eject the plate. When do you think we're going to insert the plate? Who's constructor? StampStream's constructor. As I said, it's only a couple lines, but one of those lines is insert plate. The plate needs to know its columns and rows. Is that information provided? Yeah, it's right there. When you create a stamp stream, you give it its height and its width, and it'll insert plate. When do you think the eject plate comes? The destructor. When it goes out of scope, absolutely. So that's where you have insert plate, that's where you have eject plate. All of this stuff, so let me be very specific about what all this stuff is doing that you don't have to write. All this is taking all the stuff that's thrown in the chevrons and it's putting it into this buffer for you. All you have to do is write the sync function, because what happens is when there's like an ENDL, what happens when you call ENDL? Calls flush, yes? When it calls flush, it calls pubsync, and pubsync calls sync, and you write sync. Using the magic of polymorphism, it doesn't know whether it's pointing to a stream buff or whether it's pointing to a stamp buff, it's just going to run that object sync function. And your sync function is going to empty this thing with a bunch of set die and stamp calls. You don't even have to figure out when to call sync. That's done for you. All the code's been written. You're inheriting all the code that automatically detects when this thing is filled, and when it's filled, it calls your sync function. So once your sync function is called, you can assume it's filled. Or if it's not filled, ENDL could be called before it's filled all the way. Then there are some pointers associated that let you know how much of this has been filled up. So what you should do between now and Monday is I would look at the StreamBuff class and focus in on all of these functions that are available to you. Note, can I get it all on the screen? I'm going to shrink it just one more time. These two, still can't. Well, all right, so I can't quite get them on the screen at the same time, but look at these two headings. Protected member functions, virtual protected member functions. As I said, virtual protected member functions are an invitation for you to write your own versions of them. What is this an invitation for? You're writing your own derived class. So the key is you're inheriting, and protected means that you're the audience since you're the one writing the derived class. An invitation to write your own function, meaning all this stuff down here. You're invited to write your own sync function. But what are you invited to do with these? Use them, exactly. And what these do, I would say that these are kind of the key ones here, the output sequence. These are all pointers to the beginning, to the current, and to the end. What do you think it's referring to with the beginning, the current, and the end? This buffer. The beginning of the buffer, the end of the buffer, and where the current position is. So you use those functions to initialize this buffer. You can tell it how big you want it to be. And you call, sync is called, and you need to flush this thing out. You go from the beginning to the current position. Or if it's full, you go from the beginning to the end. And then there's a way to reset them all the way back so that it can then be filled up again. Okay? So, and let me say it again. What I need you to do over the weekend is spend some time looking at these functions for the StreamBuff class and try to get a better feel for them. You don't need to overload all of them. In fact, most of them you don't. Even though these are all virtual protected member functions, there's maybe 2 that you're concerned with. But look at them and try and determine what the 2. I already told you what one of them is. One of them is sync. And then look at these protected member functions. Look at how you use these. You're not interested in input. We're dealing with output, so you're only interested in these here. Try to get a feel for how these work, and then we'll pick it up on Monday. Okay? All right.